Okay, so while Roxana is figuring out her sharing, let me do a formal introduction to Roxana. So Dr. Roxana Bujak is actually a researcher in Los Alamos National Lab, and she generally works on vector field topology with application of TDA. Today we are going to talk about application of TDA in vector field analysis and visualization. Specifically, Dr. Roxana Bujak is a staff scientist at the Data Science at Scale team at Los Alamos National Lab. And she graduated in mathematics and computer science and received her PhD in the image and signal processing group at Leipzig University in Germany. And then she worked as a postdoc researcher at IDAV at the University of California, Davis, and the computer graphics and HCI group at the Technical University of Kaiserslautern. Her research interests include visualization, flow fields, data science, sustainability, communication of science to broad audience, feature detection, pattern recognition, moment invariance, HPC, massive data analysis, Lagrangian flow representations, color theory, visualization in the environmental sciences. So that is a very broad range of topics in data visualization. And today, her main goal is going to talk about our theme today for the guest lecture is on vector field topology. So think about it as a TDA's application in the analysis and visualization of vector field data. And specifically, her talk will provide an introduction to the vector field topology, both from the theoretical side and the way it is typically treated in visualization. It also contains a hands-on part where she will use the filter, which is Vtk vector field topology from the visualization toolkit Vtk through ParaView's programmable filter. So that's why we have this link over there. If you want to do this hands-on, using ParaView alongside with her demo, you could install your ParaView and then download the file that she just shared over a Google Drive. Okay, let's get started. You just let me know when you need we need to go to the next slide. So
all right, I will do that. Okay, thank you very much for the invitation, and sorry for those technical problems. I was hanging out in the Google Meet thing by myself for a while, so we missed the time in which we could test the actual slides and stuff. So yeah, let's try it this way. Yeah, my name is Roxana Bujak, and I will talk to you about vector field topology, give you an introduction of the theory behind it for a little bit, and also was planning, and I hope we will get that to work on a little hands-on part at the end. Next slide. So what I would like you to do is check out the material which I have uploaded, and the link should be in the chat. If you joined later, I will just post it again. So you will find a README there that has the instructions. So I would recommend everybody for now to already start to download ParaView 5.9 and install it on their machine so that we can then go through those things all together. It should be kind of straightforward. The link to the download page is in the README. Okay, next slide. We will start out with some motivation for why vector field topology is important. Next slide. Vector fields are a very common phenomenon in physics and in engineering. Pretty much everywhere where some gas or some liquid comes in contact with things that are of interest to us humans, it's important for the scientists and the engineers to understand how the forces interact between those fluids and the parts that they are engineering. Next slide. The challenging part about understanding how that works is that most fluids are actually invisible. And it's kind of our job as visualization scientists to make them visible for the engineers and for the scientists so that they can learn and understand how they work. Actually, it's kind of a good thing that they are invisible, because if you would imagine that like the air in this room or something, you know, would not be transparent, then we would not be able to see anything. And this is actually a common theme that we face as visualization scientists. That is, if we draw too many visualization elements, then we again do not see anything in the picture. So what we really want to do is come up with a way to visualize the flow in a fluid in a semantically meaningful way. So we only want to show the things that are really of importance, that really have information, and not all the stuff that's just around it, it's just clutter. Next slide. And one of the most promising techniques to this goal is vector field topology. Because it has the power to really condense the fundamental structure of your flow into a sparse and easy to read representation. And yeah, in this talk, I'm going to provide you the basics of how vector field topology can be used. Next slide. We will start out with the theory, and later I will come to the actual practical way in which we use it. Next slide. The theory of vector field topology is closely related to the theory of differential equations and dynamical systems. And the things that I will be talking in this section about are mostly found in this book here by Lawrence Perko. And I would recommend, if you have, questions or want to understand things a little bit more in detail, this is a really great book with nice illustrations. So go there. Next slide. Okay, let's start out with the basics. Vector fields and streamlines. A vector field is a multidimensional function that goes from a real space or to the D to itself, and it maps X to a velocity at this point X, which you can think of illustrated like in the picture on the top by just a bunch of arrows that show the direction in which the water is flowing at that point. And a trajectory, or also called a streamline, is a line that is everywhere tangential to the vector field. That means it is a solution to the initial value problem described by the derivative of the location equals the velocity of the field at this location. And the initial value problem, according to this, is that for some time, like start time t0 and some start location x0, like I seed my streamline exactly in that point. And on the bottom picture, you can see examples of such streamlines. They are color-coded that if you integrate toward the future, usually in practice, you do this with a Runge-Kutta scheme, the color goes red, and if you integrate into the past, the color map is blue. All right, next slide. The question arises, do these types of solutions always exist? And that is something we get from the theory of dynamical systems and differential equations. If our vector field is continuous, then a solution always exists. And if our vector field is Lipschitz continuous, which is a condition that is stronger than continuity, but not as strong as actually the claim for the vector field to be continuously differentiable, then the solution is unique. And Lipschitz continuity is described as in this formula here: for all points x and x prime in my domain, I can find some constant m. Actually, it's the other way around. Like I can find a global constant m, so that for all points x and x prime in the domain, the norm in which the velocity differs at those points can be limited from the top through the distance of those points multiplied with this constant m. Next slide. Okay, so this formula here on the top is the definition of a dynamical system. I think in order to better understand what that means, it helps to think of it in terms of the streamlines. Because for us in the interested in vector fields, this function psi that shows up in the definition of dynamical system actually is the function that follows a streamline. So it's the function that follows like where a massless particle is advected to if I just let it go by the flow. And this function psi, so it maps a location and a time to another location. So it tells me if I release a particle at some starting time and starting locations, where will I find it after some time has passed? And the two properties that this function has to satisfy is first, if I do not let any time pass, I'm still at this location. This is what that first equation tells us. And the second equation tells us if I let some time pass, take a look where this particle has moved to, let some more time pass and look where it goes then those mappings psi add up to the same thing as if I had just like let the particle go for the whole time. Every dynamical system defines a C1, so a differentiable vector field, through the relation that the derivative with respect to time of this function psi, so the derivative of the streamline, equals the vector field, which is the same thing as the equation that we saw for the vector field before. Next slide. Conversely, given a vector field, its streamlines will be a dynamical system if and only if for all starting locations x0, this mapping psi is defined for all times t in the real numbers. And that is actually not always the case. I show you one example here. So if you take, for example, the vector field that is defined by the derivative of x is x squared, and the initial condition shall just be that at time 0, we shall be located at 1. So this is not just a one-dimensional example. You can put everything you want in the second dimension. In the picture on the right bottom, I put y in the second dimension. So this is how that vector field would look like. And it has a unique solution, 1 over 1 minus t. And on the top picture, you can see how this solution looks like over time. And it has this asymptotical behavior as you go toward 1. So this solution is only defined for t that lives somewhere between minus infinity and 1. And therefore, it does not exist for all t for all times. So this would be an example vector field that is not a dynamical system. Next slide. This class is about topology. So I think it's very important to introduce the concept of topological equivalence in vector fields. For that, we first need the notion of a homeomorphism, which I'm sure you are all familiar with. It is a continuous function between topological spaces that has a continuous inverse function. And once we have the concept of a homeomorphism, we can talk about the equivalence of two differential equations. So we have two differential equations here, which are both vector fields. And they are said to be topologically equivalent if there exists a homeomorphism that maps the trajectories of one of those systems to the trajectories of the other and preserves their orientation by time. An example of how that looks like are those pictures on the right. Those two vector fields are topologically equivalent. So you can pretty much see that there is this intersection of trajectories. I mean, it looks like an intersection, yeah. So if you just go straight up on the top image, right, this trajectory would be mapped to the trajectory on the bottom that also starts at this intersection and goes to the top. And you can see how you can smoothly morph one into the other pretty much. Those two are equivalent. Next slide. For ellipses.
So when you say the two trajectories should have like the same orientation, does it mean that there's always some global rotation of trajectory one that immediately superimposes it on the other one?
It pretty much is an additional restriction. If you just talk about the curves per se, right? There's not enough information in that, because you could say, if I move forward in time, I go to the left, or if I move forward in time, I go to the right. And so it's just that this time orientation is the same, that forward points into the same direction. So like with the color coding we saw earlier, that red would be on the same side for both vector fields. Yeah, thank you for the question. Feel free, everybody, to ask questions in case you have some. So, but now comes a really neat thing, and that is, for any Lipschitz continuous vector field V, I can construct another initial value problem by just dividing V by 1 plus its magnitude. And this new this new differential equation actually is topologically equivalent to my original one. Like the curves are all the same. I just pretty much change the speed in which I go along the trajectories. And this guy always has unique solutions that are defined for all times, and therefore it defines a dynamical system. That means we can always think of a vector field as a dynamical system and vice versa, or we can also think of them as just a set of curves that fill the plane. Next slide.
Roxana, I have a question for the slides too.
Yes.
So this transformation is only applicable to Lipschitz continuous vector fields, right?
So I think it is applicable to more types of vector fields, but if those are not Lipschitz continuous to begin with, you cannot guarantee that the result will be a dynamical system.
Okay.
Because the dynamical system requires a certain smoothness.
Okay. So you're saying that well, I mean, in some sense, if I have a function that is, I guess, well, it's a little bit tricky, because I think if I go back to your slides earlier, you mentioned that about the sort of Lipschitz continuity is stronger than C0, but weaker than C1. So literally, does that mean that anything that is at least C1 continuous, which is it has a first derivative, this equation will hold? Because
yes.
If something is C1 differentiable, it's definitely Lipschitz?
Yes.
Okay, so basically this already cover a really large class of functions already.
Yes.
Okay, good. Okay, next slide. Okay,
so the question that researchers interested in topology of vector fields are interested most is there an easy way to tell if two vector fields are topologically equivalent? Or in other terms, is there an easy way to say that they are similar in their basic fundamental structure? And for the next part of this talk, we try to answer that question. Next slide. In order to answer the questions, we have to look at some special streamlines. So there are two types of streamlines that actually return to a point after a certain time has passed. The easiest ones are the so-called stationary points. Those are points that have 0 velocity. So v of x1 equals 0. An example of that would be found in the picture in the very center, where like the blue streamlines gather. This is a critical point. There is velocity 0. Thank you, Bay. You're awesome. The streamlines that belong to those stationary points degenerate to a single point. For all times, the streamline would just stay there if I seed it exactly in that point. The second type of streamlines that return to a point are the so-called periodic orbits. They have non-zero velocity and return to the point periodically, so after a certain time has passed. Exactly, you can see one there, which is this red circle on the outside. If I see the streamline there, it will just go in circles for eternity. It will never be able to leave that circle. And yeah, this complicated looking formula just tells you the periodic, like the periodicity in which that thing returns. Okay, next slide. Critical points are stationary points that have a non-singular Jacobian or velocity gradient. So the definition of the velocity gradient you can see in the formula is just the spatial derivative of my vector field with respect to all spatial directions. So D is the dimensionality, so that's usually 2 or 3 when we talk about vector fields in practice. And the thing to be non-zero, non-singular means it should not have 0 eigenvalues. Critical points are always isolated, while stagnation points, so those locations with just a 0 velocity, they can also like be bundled up several. Next slide. The Hartman-Grubman theorem, and for the proof, I again refer you to the book by Poincare, states that a C1 vector field with a critical point at 0 is topologically equivalent to its linear part in a neighborhood of 0. So if I have some complicated higher order vector field around a critical point, I can always just look at the Jacobian to understand its overall behavior. So its overall structure. They are like all topologically equivalent to just the linear part. That means in order to figure out which vector fields, at least in a local neighborhood, right, are topologically equivalent, it is sufficient to just classify the first order critical points that can exist. 2 linear vector fields are topologically equivalent if the eigenvalues of their Jacobian have the same signs. And what that means, I will show you in the next slide. Those are pretty much all possible critical points that can exist in a 2D linear vector field. We can classify them by just looking at the Jacobian, so at their linear part, in the neighborhood of the critical point. And so whenever I have both real parts being negative, that means that from all direction, pretty much the flow is being attracted to this critical point. So I will have a sink. And the sink can have 2 shapes. The one at the very first point would be a spiral sink, which I get if my imaginary parts of my eigenvalues are not 0. Or I could have a node sink, which is the second from the right, which I get if my imaginary parts are 0. So either I have like a spiraling motion going to my sink, or I have a motion coming from all sides pretty much. If my real values are negative, I have the exact opposite. Sorry, if they're positive, I have the exact opposite, where in all directions I have repelling behavior. Also there, I have a spiral or a node source in that thing. Bay already pointed out the center. The center is a special critical point where I see, I copied the wrong formula there. So center has 0 real part and an imaginary part that is non-zero. So I think this is just the wrong formula there. And finally, on the very right, we have a saddle type critical point. This is the situation in the Jacobian when I have 1 positive and 1 negative eigenvalue in my Jacobian. So I have one direction that has this repelling behavior that belongs to the positive eigenvalue, and I have one direction with the attracting behavior that corresponds to the negative one. Okay, next slide. A similar situation occurs in 3D, but there I have a few more options because I have 1 additional eigenvalue. So on the picture on the very left, you can see a repelling node. In that situation, all my eigenvalues are positive, so everything is being pushed away from that situation, and I do not have any imaginary part. I can also have a repelling focus, which is the second picture. That occurs if I have some kind of imaginary part that always like describes the orientation. But still, all my real parts are positive, so everything is moving away from this critical point. I have 2 different types of saddles in 3D. So that picture number 3 that Bay is pointing at right now has 1 eigenvalue that is negative. So 1 axis from which I have attracting behavior, and 2 eigenvalues that are positive. So I have a complete plane that works as a repeller. So where the the flow moves away. And on the last picture, we can see a focus to settle, which is if my imaginary part is not 0, then I have a spiraling behavior there. Next slide. Those pictures look very similar, so I will not talk too much about them. The only difference is that the positive and the negative eigenvalues are reversed. So in contrast to the sources, now we have the sinks on the left, and in contrast to the 2 settles, now we have the 1 settles on the right. So these settles have one axis of repelling behavior and a complete plane of attracting behavior. So you get those 4 cases just by inverting time of the 4 cases that we just discussed. Next slide. An important property of critical points is called hyperbolicity. A critical point is called hyperbolic if it does not have any eigenvalues with 0 real part. I already showed you that 0 real part is what describes the center, and the center is not hyperbolic. Hyperbolic critical points are structurally stable. That means a small perturbation of the field, of the vector field, does not change their topology. So a settle that I slightly distort will stay a settle. There's nothing that will change. But the same is not true for the center, as you can see here. The top picture is a true center, where the streamlines that I drew in there are periodic orbits, while a very small perturbation of the field on the bottom changes that. And now this critical point is actually no longer a center, but it becomes a spiraling sink. Next slide. A very important concept to think about when it comes to vector field topology are limit sets. And those are pretty much the locations that the path lines go if you just look at them in their asymptotic behavior toward infinity or minus infinity. So a point is called an omega point of a trajectory if there is some sequence Tn that goes to infinity, so this is some sequence in time that goes to infinity, such that the limit of the flow map of psi of this mapping of the trajectories will have the trajectory go to this point P. Yes, Bay illustrates it really nicely. You can see that inside of the red circle, all the streamlines, if you follow them integration-wise negative in time, will converge to this critical point in the center. So this point in the center actually is their alpha set. So this is the end. If my Tn goes to minus infinity, then we call it an alpha set, which is analogously defined to the omega set. So the alpha set is pretty much the origin of my streamline, and the omega set is the destination if I go to infinity. And so those streamlines inside, their alpha set is the critical point in the center. If you follow them forward in time, they converge toward the periodic orbit, toward this red circle that you have here. And there, every point on that circle is an omega point. The whole circle is the omega set because I can find such a sequence Tn for each of the points, so they will converge there. Next slide. And in 2D, we have a really, really nice tool to simplify the way in which we think about vector fields, and that is the Poincare-Bendixson theorem. It states that given a differentiable real dynamical system defined on an open subset of the plane, every non-empty compact omega set, which contains only finitely many fixed points, is either a fixed point or a periodic orbit or a finite number of fixed points connected by trajectories. So this is long and complicated. It's because this property is really powerful and it's not a given. But rule of thumb, what we can say is whatever streamline I have in 2D, it either goes to a critical point, just like we saw on the top picture in the middle, or it goes to periodic orbit, right, which we saw on the circle on the top, or it can converge toward a construction like we see on the bottom image. So there is a saddle in the middle with trajectories like coming out and going to itself. And you could imagine that the outside trajectories, as they move forward in time, circle around this structure that looks like the figure 8, approximating the structure figure 8, arbitrarily close, right? But never reaching it. So the whole structure actually is the omega set of those streamlines that come from the outside. So that can also happen. But those 3 different cases are actually a very small number of different cases, and they are really pretty simple. So it's kind of nice and easy to think about. Streamlines can just not go anywhere where they want to. They will always like settle down at some kind of small finite location, the omega set. Next slide. I'm stressing so much what a nice property that is. So I want to show you why. And the thing is, the same is not true in 3D. In 3D, we have structures like, for example, so-called strange attractors. And one example is the Lorentz attractor that you can see in the picture here, which is not a complicated vector field. Like, it's quadratic, right? It's really smooth. It's super nice. It has all the properties that you could possibly ask for, but it already exhibits completely chaotic behavior. And so those strange attractors have the property that streamlines like move toward it as you integrate them forward in time. But they never really settle down in one location or in one periodic orbit. I always have the situation that if I just let time go long enough, I can have 2 streamlines that approach each other arbitrarily close. And after some other time, again, they completely get lost in this attractor and are apart from each other very far. Like, it's not super easy to see from the picture, but we have pretty much 2 planes here that have this spiraling behavior. And it's just, the particle gets trapped in one of these planes, goes around in circles for a while, but then at some point it just changes its mind, jumps over to the other plane, goes there for a while, goes back, and it never ends. So that is really very different from the behavior that we see in 2D. It almost looks like here as if the trajectories intersect each other, which is not the case, but in 3D, they can just, come arbitrarily close without the intersection happening. Next slide.
Is this a property of the equation itself, or the discrete time stepping and the inaccuracies introduced by that?
This is a property of the equation itself. The question is actually better placed the other way around. And that is, if I have only discrete integration, would the same phenomenon still occur? Or if I have only a discretely sampled, linearly interpolated version of this data set, would the same chaotic behavior still occur? And I do not know the answer to this question, actually. I think it is yes, because I looked at like 2 million time steps on the discrete version of this data set, and it still happened in exactly the same way. So I think the answer is yes, but it's not easy to mathematically prove that with the numerical error that comes in from the practical computation.
Roxana, I like your approach. I want to know the infinity and maybe sample it 2 million times.
And I really selected those 2 million very carefully, but this was the time I was willing to wait for peer review. All right. I thought that maybe this behavior would get lost in an actual discrete field, but I could not see it getting lost. So yeah, next slide, please.
Yeah, I just want to comment though. I think there have been work, we might hear some about the next lecture about reconstruct dynamics from discrete point cloud, sample from it. And I think earlier this semester, we've seen one picture where folks were trying to reconstruct dynamics of a system using RIPS or witness complexes. And I don't recall the exact conclusion, but if I were going to think about it, is I think there was some scenario where if you don't have sufficient points, then tools, for example, like persistent homology wouldn't be sufficient to recover any of the underlying dynamics. It might recover that there's some loop structure, but it does not have sufficient data to recover its dynamics. So I think another thing where I've seen people down is that in order to recover the dynamics, they have the point cloud sample of the system, but also for every single sample, not just having X, Y, Z coordinates, but also a timestamp. So that additional information will also help with the reconstruction process. Anyway, so that's a side note. Go ahead.
Next slide.
Oh, this is a new one.
Oh, sorry. Yes, there we go. Okay, so the most interesting topological features are critical points and separatrices in vector fields. And while the former are defined exactly in the literature, the latter, interestingly, are not. So I really tried to, pin things down with the definition of separatrices, and I came across like 10 different definitions or so. And I found that very, very interesting, because in the way we think about it in practice, right, we always have a very clear image in our heads what we're talking about. But actually, when we talk about theory, it's not so simple. I want to talk about the theory by Marcus in 2D to show you what separatrices are in this case, and kind of leave the 3D question open, because I do not know the answer, and I think the dynamical systems people also do not know the answer to that question. Coarsely speaking, separatrices are solutions, so they are trajectories, which differ from their neighbors either in their limit sets or in their behavior at large, is what Marcus is writing. Next slide. Quick literature recommendation. This is the paper I will be talking about now by Marcus from 1954. Really groundbreaking work. Very important, I would say. And crazy that I have never actually come across that in, at university or as a visualization scientist. Next slide. So Marcus defines parallel regions. A collection S of curves filling a plane region, R, which is a subset of the plane, is parallel in case S is topologically equivalent to one of these following three cases. The first one is called a strip region, which is just the plane filled by parallel lines. The second one is a punctured plane filled by concentric circles. And the third one is the punctured plane filled by rays from the deleted point, which is also called a spiral region. So it's pretty much the spiral sink version that we saw earlier for the spiral region. It's the center for the annular region. And it's just the regular streamlines for the strip region. Next slide. And yeah, now it gets a little bit technical, but a solution curve S of a differential system, fancy S, defined in the entire plane is a separatrix. So this is what Marcus defines the separatrix. In case S is not embedded in a parallel neighborhood N, such that all the solutions of this parallel neighborhood have the same limit sets in forward direction S plus, so that would be the omega limit set, and in backward direction. And also this neighborhood N is bounded by the limit sets, like at the top and at the bottom, and exactly two solutions, S prime and S prime prime, so two other trajectories on the sides that also have the same limit set. So that's very, very complicated, but yeah, if you take a look at the different definitions of separatrices, you kind of see what he wants to do. So if the best way to think about it is really go back to the intuitive the way that he said, we want to have locations, where a trajectory differs in their limit sets from its neighbors. And it's pretty much what it is, just in a more rigorous way. Examples of separatrices are critical points, because as we saw earlier, if I seed a streamline in a critical point, it stays there forever. While if I seed a little bit off, right, then I go maybe forward to that critical point in time, maybe backward. I have a different behavior of the neighbors. Separatrices are also periodic orbits. Periodic orbits, right? They have themselves as the limit set, while the other trajectories that you see the little bit tiny place off, either positively or negatively in time, go away from the periodic orbit and will end up somewhere else. And the invariant manifolds of saddle type critical points are also separatrices. So remember, the saddle type critical points are the ones that have a positive and a negative eigenvalue. And the corresponding eigenvectors provide the direction of the strongest attraction and the strongest repelling behavior of that saddle. And the invariant manifolds of the saddles are these only two streamlines pretty much, or four, that really reach the saddle. So the red ones and the blue ones, the base pointing out, those are the ones. Every other streamline will never end up in the saddle or will never originate from the saddle. They can get really close, right? But they will never go there. And those specific streamlines, they are called invariant manifolds of the saddles because they're invariant by the flow, they form a manifold, and they enter the saddle. All right, so like those are the three intuitive types of separatrices. Next slide. But we can also have less intuitive separatrices. There are dynamical systems that do not have any critical points, but still have separatrices. And here is an example of that. On the top right picture, you can kind of guess where the separatrices would go. On the bottom picture, I drew them in, and you can really see where they are. And the reason that we know that they are actually separatrices, you can find on the pictures on the left. And that is, this vector field is an analytic vector field, and I can expand it all the way to infinity by using some fancy transformation that transforms the plane onto a sphere. And this is actually the sphere with the vector field transformed there. And this sphere has critical points, and they belong to critical points at infinity, if we just talk about the plane. And two of those are actually saddles and produce those separatrices that if you project the whole thing back from the sphere, then form this red and this blue line that are separatrices in infinity on the plane. So there are separatrices that are more complicated than the simple ones that we just looked at. Next slide. And now comes this really, really groundbreaking thing that Marcus proves in his paper. And that is that in 2D steady vector fields, the separatrices segment the domain into what he calls canonical regions, which are those three types of flow that we looked at earlier, in which all path lines are parallel. So if I'm able to extract the separatrices, then I know that I can really think of my flow, no matter how complicated. Pretty much it's just built out of Lego blocks, pretty much. And I only have 3 different types of Lego blocks. So it really breaks down, no matter how complicated your 2D vector field is, the whole thing into something that has only these 3 fundamental canonical shapes. It's very easy to think about it that way. And it's also very easy to think about the original question that we had. When are 2 vector fields topologically equivalent, right? And that is pretty much if I extract all the separatrices and I find a homeomorphism that maps my separatrices of one vector field to the other with each of those segments that I get having the same properties inside, then I know that my vector fields are topologically equivalent.
I have a question.
Yeah. You were looking like it already. I was like, Bay looks like she has a question.
Yes, I do. So is it always true that in the middle region, there's always contains a spiral region? Like by default, like this 2 type of regions always nested? Like there has to be, you know, I mean, when I'm away from this pinched point, I basically would end up having some sort of spiral region. Is that true?
So the annular region does not have a spiral region. This is like around the center. It's just like a set of a bunch of periodic orbits.
Right. Also, you're saying that this thing here is actually a center, not a spiral.
Yes. Yeah. Those two are different. One is center. One is a spiral. This is what makes them topologically different.
Okay. Okay. That makes sense, because I was just looking at the glyph. I saw this middle thing is a spiral, but it's not. But it's actually it's an honest to God center in the middle.
Yes.
Okay.
There's a question in the chat. Can you show the canonical regions from the last vector field?
Oh, okay. Let's go there. Yes. So it's pretty much the three regions that you can see. Those two separatrices split the thing up into. So you have the middle region, which is a strip region. And the top and the bottom one, they are also strip regions as far, no, wait. They are not strip regions. Maybe if we look at infinity, they are spiral regions, actually, just without the spiraling part, or with a very small spiraling part. If you look at the sphere thing, you can see this red point. This is the pinched out point to which all the trajectories go, right? And you can see a little bit of spiraling as it approaches the separatrices. So there would also be a separatrix mirroring the top one going to the bottom that would really like form this circular point. Yes, I think that is the way. We have two spiral and one strip region here. Good question.
Quick question about that visual. So is it a plane sort of mapped onto a sphere in terms of spherical coordinates? Like,
so the way that this mapping is done is you take the plane, you embed it in 3D so that it intersects the z-axis at 1 and is parallel to the xy plane. And then you draw a straight line through the plane and map the vector to the place where this straight line intersects the sphere, the unit sphere. So the North Pole pretty much is identically what it was before, and infinity is mapped to the equator.
okay, so there's nothing on the other half of this.
The other half of the sphere is a copy of the top half of the sphere, just with, I think, the direction inversed.
Okay.
Yeah, so this is why in that picture, in the second one, I did not draw the separatrix as it goes on the southern hemisphere, because the northern one pretty much has the complete vector field. And yeah, all the equator is infinity. And you, like, there are other ways in which you can have a projective connection between the plane and a sphere, right? So for example, the normal way, you would just map infinity to the North Pole, right? But this specific type of projection is more helpful because it does, like, usually you have higher order critical points at infinity. And if you map the whole infinity to just one point, then you would have in this situation 3 critical points at infinity. While if you map it this way, then they are nicely separated and you get a better understanding of what's happening. In the Perko book, there is a complete chapter about this, this projection, and also how it would extend to 3D actually.
So Roxana, I need to give you a time warning. We have 21 minutes left for the remaining of the class.
All right, then it's probably not a huge deal if we do not get my sharing to work, because we would manage to get to the hands-on part. But I can try. I'm almost done. So this is the end of the theory part. This is what I wanted you to know from a mathematical perspective. This nice behavior that we just saw in 2D, again, does not hold in 3D. I do not have like a really great explanation or something for that, except for the example of the strange attractor that I showed you before. If we do not have this asymptotic behavior that we have in 2D, we also cannot easily define separatrices in the same way. So what do we do in practice? Next slide. In practice, our data in scientific visualization is almost always composed of 3 distinct parts. Most of the time, they are represented separately. And those 3 parts are, first, a finite set of points, the domain of definition D. They form a discrete subset of physical space and would be represented by the nice dots on the top. Second, a neighborhood relationship amongst these points, or how we would refer to a grid. And third, one or more functions that map points of D into other spaces. So in this example here, it's a scalar function. In our example of vector fields, right, those functions would be vector valued. Next slide. And in scientific visualization, we treat vector fields defined as fields, as discrete fields on a discrete set of points in a grid, and we interpolate usually linearly or multilinearly within the cells of this neighborhood relation. That makes things for us really nice and easy, because a piecewise linear or multilinear function is always Lipschitz continuous. So that means we always have streamlines that exist for each point in a unique fashion. So that's a great help that we do not have to think about those basic problems to begin with. Next slide. The next thing is that we think about our vector field to be piecewise linear. We can explicitly make use of the linear interpolation when it comes to the extraction of critical points. That way, the locations of the critical points can just be computed analytically for each cell by, inverting the formula of the linear interpolation, and there you go. Also, there can actually not exist any higher order critical points. I mean, we already saw that even in the general case, it is sufficient in a neighborhood to look at the linear part to classify your critical points. But now we know we actually do not have to look at anything else, because nothing else can exist to begin with. Next slide. And the way in which we detect the separatrices is also a little bit simplified. The algorithms usually focus on the stable and unstable manifolds of the saddles, so the invariant manifolds of the saddles, and ignore the other types of separatrices that could possibly exist, because it's easy and fast and robust to extract them, while with the other ones it's like really unclear how you would go out to detect those. This trick that I showed you with the sphere for the critical points at infinity, that only works for analytical critical points, actually just for polynomial ones. And the other thing is that those invariant manifolds, they also exist analogously in 3D. I do not have to think about complicated strange attractors or something if I just look at the surfaces and lines that originate at the saddles. Next slide. So vector field topology in practice as an algorithm pretty much looks just like this. We detect all critical points analytically in each cell. We classify them based on the eigenvalues of their Jacobian, just as we learned before, and they're all linear, so it's really easy. And then we seed separatrices in a small offset of the saddles in the direction of their eigenvectors. In 3D, we would also seed separating surfaces. So if I have a saddle, that has one repelling axis, one attracting surface, right? I would seed a stream surface in a little circle inside of this plane and integrate that one. And then I hope in the end I get a nice segmentation that kind of resembles the one that Marcus is describing. Next slide. And the visualization toolkit Vtk is an open source C++ visualization library and the foundation of many tools, like for example, ParaView or Visit. It also has a vector field topology implementation that I wrote actually, and it's the class called Vtk vector field topology. And this is the link where the documentation is. I also put it into the folder in the Google Drive. It is accessible through ParaView and its programmable filter. And I was hoping to show you how that works, but I don't think I can share my screen. So let's skip that part maybe and just move to the next slide. The instructions you can find in the Google Drive. And if you just follow them, you will be able to just use it by yourself. So we skip the hands-on part and go to applications. Next slide. This is an application of groundwater. And the groundwater researchers, right, they use hand-drawn images like the one on top, which of course is a really, really tedious situation. What you can see there is pretty much different basins that are like lakes or something, or a mountain terrain where like rain comes in. So some of this top thing has like a source type of behavior because it rains there. And some of the regions have like a sink type of behavior because it's like the origin of a river where the flow moves away, right? And the vector field topology would actually give you the picture on the bottom that gives you the exact locations of the separatrices where those different basins differ. So what it would mean here is that in each of these compartments that Marcus has told us exist, I have flow that never mixes with the flow from the other compartments, as long as our model is steady, right? So if I have, for example, some spill, right? I know it's completely confined to one of these compartments. It will never like go outside of those buckets. Also, it tells the groundwater researchers that along those separatrices, water meet that has different chemical components. So it's very likely that we get some chemical reactions along those separatrices that they're interested in studying. Next slide. Now on the bottom, you can actually see the final segmentation that is based on the trajectories, where the color just, or it's just an ID to say this is this basin, this is this basin. And the researchers can use this segmentation to derive statistical properties of all the different segments, like how big is this segment, what is the distribution of chemicals, how strong is the flow rate there, how long do particles take to get from one place to the other, and answer questions like this. Next slide. This is an example of a water cleaning simulation where we think we might have some dirty water, some spill or something, we want to clean it. So the blue dot on the top picture is a sink where we suck out the water, put it through a cleaning process, and reinsert it into the ground at the red point where there's a sink. And the question is pretty much, are we getting all the water clean with this way? The background of this flow moves a little bit from the left to the right. And so we get this segmentation if we just look at the vector field topology. And you can see the region in the middle, the yellow one, this is water that we released after cleaning, but it actually goes right back into the sink where we suck out the water. So we pretty much repeatedly clean the same water in that middle part. While there is another region that comes from the left boundary and goes into the sink where we get new water that is dirty that we will clean. And on the top part, there is some water that we released from the red source and that will go out to the right. And apart from this, on the very bottom and on the very top, we have two layers of water that will just never be cleaned at all. They just pass by. And in the bottom picture, you see an example of a 3D version of the simulation where the two saddles now not only give rise to one-dimensional separatrices, but actually to those separating surfaces. But the behavior is the same. Next slide. This is an example from space weather, a Magneto hydrodynamic simulation that simulates the magnetic field around the Earth and the Sun and how they interact during solar storms. And in the 2D version of the data set, you can see the red and the blue dot are the magnetic north and south pole of the Earth. So the Earth is really small in the picture. And from the, what is that, right is the magnetic field that comes from the sun that interferes with that. And you can see how it splits the whole behavior into regions where we have magnetic lines that like come from the North Pole going to the South Pole of the Earth and vice versa, depending on your direction. We have places where they come from the Earth, go into the universe. And we also have places where they never touch the Earth at all, where they just pass us by. And on the bottom, you can see a three-dimensional version of that thing, which gives an additional insight, and that is those two regions of this center type of behavior around the Earth is actually just one region that is connected. Just in 2D, it looked like it were two separate regions. All right, yeah, and topology could also aid automatic plasmoid detection, which is some kind of compactly bounded magnetic reconnection features that like happen if there is a solar storm. Next slide. Well, I think this is a good time to stop because I think that gave you a really nice overview over what vector field topology means in theory, but also in practice for the steady case. And there's a whole big extension to time-dependent flow, but I think considering the time, I would just give you the literature recommendation to the state-of-the-art report that Bei and I wrote, if you're interested in how this whole concept would translate to time-dependent vector fields. All right. Do you have any questions?
Well, let's give a round of applause if you can unmute or using the virtual hand. Thank you for an amazing talk for the day. And I'm glad we overcome some of those technical difficulties and then be able to. So any questions? Feel free to unmute yourself or type in your question on the chat. So I have a question while people think about other questions they might have. The groundwater, is that new work? I have not seen that work before.
Oh, yeah. I mean, it's kind of, we tried to actually we just got it rejected. There was a guy from Korea that reached out to me because he was looking for an implementation of the vector field topology because he had like this picture on the top and he wanted an automatic way to extract that. And yeah, I think he tried to contact Holger Teisel and Tino Weinkauf first because he had read their papers and they said, yeah, talk to Roxana, she has like an implementation. So